So, as you might notice, you are not currently in the room with me. So I sent out this email indicating that I have a sudden emergency, but I have enough time to get some recordings made in advance. So I'm going to get some content out for you to look at in lieu of coming to physical class. Let's do that right now. So we talked about last time is the distance formula for points in the plane. And that let you say, given 2 points, what's the length of this line between them? And we got that formula. Sorry, let me close the door. What I'd like to do today, well, next, this isn't the only thing, is how do you find this point, the point that's exactly halfway between them? And maybe the right way to do that is starting with points on the line. So the midpoint between two numbers, so if you have two numbers A and B, numbers just on the line, what's the number that's halfway between them? And you already have a name for this. It's the average between those two numbers. It's given by add the numbers up, divide by 2. For example, you want to find the midpoint between 4 and 10. 4 plus 10 over 2, well, that's 14 over 2 is 7. And maybe just to visualize that this is correct, well, if there's 4 and there's 10, let's see, 5, 6, 7, 8, 9, 10. 5, 6, 7, there's 7. Yeah, that looks about right for halfway. The midpoint between 2 points on the plane is given in terms of coordinates by just doing those instructions to the x and y coordinates. The midpoint between a point x1, y1 and x2, y2 is add up the x coordinates, divide by 2. There's your new x coordinate. Then add up your y coordinates, divide by 2, there's your new y coordinate. And let's just check that this does something reasonable by finding them. Let's find the midpoint between these two. So the midpoint, there we go, may as well give a reasonable variable name, is add up the x coordinates, sorry, this button needs to be pressed. Add up the y coordinates, 3 plus 1 over 2. And let's just simplify that out. Minus 3 plus minus 1 is minus 4, divided by 2 is minus 2. 3 plus 1 is 4, divided by 2 is 2. And to see if that's correct, let's graph those things. Yeah, okay, let's do it right here. So, let's just sketch these points as best we can. Negative 1, 3 is negative 1 in the x direction. 3 in the y direction. Negative 1 is negative 3 in the x coordinate, plus 1 in the y direction. The midpoint was allegedly negative 2, 2. Yeah, that looks like it's halfway between those two lines. It's the midpoint of that line segment between. All right, cool. So the midpoint, we have now access to a midpoint formula. In order to walk our way towards functions, let's talk about equations. So what do you mean by the graph of an equation? So an equation with two variables, 2x minus y equals 6, what does the graph of that mean? Well, it just means all x, y, x comma y points, right, an x and a y value gives you a point in the plane, with this equation, 2x minus y equals 6. So that means that it's easy to check if a point is on the plane. If you want to see if 2 comma 6 is on the plane, plug in this x value, that y value, see if it works out to be 6. You'll get 2 times the x value is 2, minus the y value is 6. You work that out a little bit. 4 minus 6 is negative 2. This is not equal to 6. So what can you conclude? 2 comma 6 is not on this graph. You know, 5, 4, same thing. I'll encourage you to pause this video and do it yourself right now. Cool. Pause it now, and we're back. So, what do? You plug in x equals 5, y equals 4. 2 times 5 minus 4. You would like to know, is that equal to 6? So, let's do that. 2 times 5 is 10, minus 4. Yeah, that's 6. So what's the conclusion? 5, 4 is on the graph. So that's what it means to be on the graph of an equation, but how do you actually generate the graph of an equation? Well, one way to do it is just by finding enough points to get an idea what the graph looks like. So here's what we'll do. Here's one. 2x minus y equals 6. We can find y values that correspond to each x value. Let's plug in x equals 0. So this will give us, right, this whole vertical line is x equals 0. Those are all the points with x coordinate 0. Let's figure out what y value solves this when x is 0. So doing that, let's see, you get 2 times 0 minus 6 equals, 2 times 0 minus y equals 6. 2 times 0 is 0, so this just becomes y equals negative 6. So the point 0, negative 6 is on the graph. Let's find that. 0, 1, 2, 3, 4, 5, negative 6. There's a point on the graph. X equals 2. Let's see what happens with that. So 2 times the x value is 2 minus y equals 6. Let's see, I guess I should add that y to the other side and subtract the 6. 4 minus 6 equals y, negative 2 equals y. So 2 comma negative 2 is on the graph. 1, 2, 1, 2. There's a point on the graph, and let's just keep on going. X equals 4. 2 times 4 minus y equals 6. Going through the same motions to solve. Maybe we'll go through different motions. Let's subtract 8 to the other side. Minus y equals 6 minus 8 is 2. Is negative 2. Deal with the negative sign. That means y must be positive 2. Right? Multiply both sides by negative 1. All right. So we see here that 4 comma 2 should be on the graph. 1, 2, 3, 4, 2, and one last one. When x is negative 1, and right, as with all of these, you should have done these in advance, but do this one in particular in advance if you haven't already. Do this last one, then come back. Cool. Plug in x equals negative 1. 2 times negative 1 minus y equals 6. Well, 2 times minus 1 is minus 2, so that becomes minus 2 minus y equals 6. Add 2 to the other side. Minus y equals 8. Multiply both sides by negative 1. Y equals negative 8. That looks like negative 1, negative 8 is on the graph. And, well, here's the last one. So now that we have some points, let's try to interpolate the shape of the graph by connecting these with, let's just use line segments right now. And one thing you might notice, if you did a better job plotting those points than I did, this chart looks like a line. A line. And we'll come back to that soon. This equation right here is an example of what's called a linear equation. Oh, sorry if some of that was off the edge of the screen. It should all be on screen now. And, well, you can pause the video if you need to double check that you have stuff that agrees with what I read. Nice. So let's graph one more. So definitely pause this one now. Fill in this table for the equation y equals x squared over 2. Cool. You've done it now. Let's fill it in. And one thing is already filled in. When x is negative 3, y is 4.5. Negative 3, 2, 3, 4.5. There's a point on the graph. Negative 3, 4. Filling in the rest of the table, which you've already done. Y equals negative 2 squared over 2. Negative 2 squared is 4. Divided by 2, you get 2. Negative 2, 2. Negative 1, well, you've already done this. Y equals negative 0.5 or 1/2, whichever you prefer. So when x is negative, oh, it's positive, isn't it? Yeah, positive 0.5. Negative 1, y is 0.5. 0 results in y equals 0. And maybe here's an interesting trick. You notice that the first thing you did in each of these computations is you threw out the negative sign anyway. So I think I already know what happens here. You get 1 comma 1/2. When you plug in 2, you'll get 2. And it'll be for the exact same reason as you got 2 right there. And let's maybe just try to interpolate between And maybe you even recognize a general shape for what this graph is. This is a shape called a parabola. It's something we'll look at a lot soon. So whenever you have an equation, you can graph it. You can do it by plotting a bunch of points. You can also use a computer to get an idea. And we'll maybe do that exactly for this. Let's pull up a tool. The tool that I like to use. Let's graph y equals x squared, and then divide that by 2. Yeah, that looks pretty close to what we had. 0, 0. When you plug in 1, you get 0.5. Plug in 2, you get 2. Plug in 3. Four and a half. Nice. All right, carrying on. Intercept. So here are some definitions. Here are 2 notions. And I have 2 lines because there are going to be 2 things that I'll write down. The x-intercept of a graph is all points where the graph crosses the x-axis. For instance, here is the graph of an equation. It happens to be the equation 2x squared plus 3y squared minus 4xy equals 5. By looking at this graph, it looks like the x-intercepts are about, well, it's like negative 2.2-ish, comma 0. And notice, I want points, so I want xy coordinates. I know it's on the x-axis. Things on the x-axis have y coordinates 0. Negative 2.2 and 2.2, comma 0. So that's what it means to be an x-intercept. It's where the graph crosses the x-axis. To get the y-intercepts, well, the y-intercepts are all points where the graph crosses the y-axis. And let's go through and find them. We can visually identify them. And again, this graph isn't so accurate, so we can't be too trusting of the exact values we'll get. It looks like the y-intercepts we get are about, what's the x-coordinate 0? Let's go with the negative 1 first. Negative, I don't know, that's 1.6-ish. 0, positive 1.6-ish. Neato. So, what does all this mean algebraically? Well, given an equation here, is there a way we could find these? So let's think about what it means to be on the x-axis. To be on the x-axis means that the y-coordinate is 0. So it's all points, x comma y, on the graph, with y equals 0. So if you want to find the x-intercepts, plug in y equals 0. And if you have an equation for this graph, well, you can plug in y equals 0 and see what happens. This equation will become 2x squared plus 3 times 0 squared minus 4 times x times 0 equals 5. Oh, neat. Well, anything times 0 is 0, 0 squared is 0. So this really just boils down to 2x squared equals 5. X equals 5 halves. X squared equals 5 halves. So x equals plus or minus the square root of 5 halves. So, even before we get a decimal approximation, because we will in a moment, you notice there's a plus or minus. The x-coordinate looks like x-intercept. There are 2 of them. One of them is positive, the other one is negative, and they both have the same size, the same absolute value. They're just plus or minus the same number. Let's get a decimal approximation here. Again, using a calculator. Square root of 5 halves. Something here is suspicious, is it not? So let's see, I plugged in y equals 0. This equation became that. I got x equals plus or minus 1.6, which is in fact there. I think this is not the right graph. I think that I may have, when I graphed this using a machine, swapped the x's and y's. Nice. But according to this, the x-intercepts are about 0. And maybe we'll even use this notation, plus or minus 1.6. How can you find the y-intercepts? We'll do the exact same thing. Find the y-intercepts yourself, and then come back. Well, I guess you can't come back, because I haven't written what's up here. All right, so what are the y-intercepts? If I want points on the y-axis, well, I want all points on the graph, but on the y-axis, what does it mean to be on the y-axis? It means you have x equals 0. So, let's see. And if I did accidentally swap the x and y values here, then I think I should get things that are about plus or minus 2.2 for this computation. Let's see what happens. Plug in x equals 0. Let's see what we get. We will get 2 times 0 squared plus 3y squared minus 4xy equals 5. I'm beginning, right, and plug in x, all of x zeros for all of the x's. 4 times 0 times y. And again, those cancel. 3y squared equals 5. Y squared equals 5 over 3. Y squared is plus or minus root 5 over 3. Going now back to the calculator. Oh, and I'm sorry, I screwed up again. I'll write down this, y about plus or minus 1.3. So the y-intercepts we have are x is 0, y is plus or minus 1.3. And maybe you noticed this error that I made before. I certainly didn't mean to have an x-coordinate of 0 there. The y-coordinate is 0. That should have been 1.6 comma 0. And I'll click back here because I know that I failed to bring this back. Sorry, just to recap the stuff that may have been covered up. All the x-intercepts are given by points when the graph crosses the x-axis. That's given by plugging in y equals 0 into the equation. If you want the y-intercepts of a graph, it's all places where the graph crosses the y-axis. That's all points on the graph with x equals 0. So pictorially, you can read them off, and algebraically, you can compute them if you have an equation. Cool. And you know what? Well, I can't click that link using what I have here. Go ahead and see if that is this thing that's graphed. There's an error somewhere. Graph this equation. Using Desmos, that link should work. See if it's right. And maybe I'll even just do that now. May as well. I have enough time, I think. It should work. 2x squared plus 3y squared minus 4 times x times y equals 5. Is it going to graph that? Yeah. All right. All right. Y-intercept at 0 plus or minus 1.3-ish. That agrees with the computation, but not with the picture. So this picture is wrong. The x-intercepts are about plus or minus 1.6-ish. That agrees with the computation, but again, disagrees with the graph. So this, I graphed something else there. Alrighty. So that concludes that particular packet, but I want to keep on making progress. I have my eye on the time. It looks like I'm 19 minutes in. Let's start it on thinking about functions. And Well, we've seen some examples of functions just on the previous page, but let's start with a slightly formal definition. So many times you'll find yourself interested in some quantity which can be totally determined in terms of another quantity. Such a thing is called a function, and maybe we'll see an example right now. So suppose you stand on the ground and you throw a bowling ball vertically with an initial velocity of 20 meters per second. Until the ball lands, and this is underlined for a reason that will become clear soon, the height of the bowling ball in meters is given after t seconds by this formula. Height is -5 meters per second squared, if you like. This is because acceleration due to gravity is about -10 meters per second squared. Those of you who are physicists might prefer that -5 to be something more like -4.9, but even that's not exact, so I'll be happy enough with this, even through this whole class, just to make the numbers nicer. Plus some term coming from the initial velocity. And let's use this model to make some predictions. Let's see what happens when at t equals 2 seconds. So plug in h of, let's plug in 2 seconds first. I want to jump down to this one first. When you plug in t equals 2 seconds, you'll see h of 2 seconds is, let's write it out, -5 meters per second squared times 2 seconds, quantity squared, because there's t, plus 20 meters per second times 2 seconds. And there are some things you'll notice straight away. Those seconds cancel. And if you are familiar enough with how squaring works, you'll see that something's going to cancel there, but maybe I'll expand that out and we'll see what happens. -5 meters per second squared times, right, so what does it mean to square? It means you multiply the thing by itself, so it'll be 2 seconds times 2 seconds. But that'll be 4 times seconds times seconds, so 4 seconds squared. Plus, and let's just write this out, 20 times 2 is 40, and there's still some meters involved. All right, so let's carry on. You see a bit more cancellation that'll happen. Second squared cancels with second squared. Now I see -5 times 4, that's -20 meters, plus 40 meters. Yeah, that's 20 meters. So there's an example here of what I'm doing that's like just units analysis. I've made sure to plug in quantities with units next to them, because all of these things do have units. Time isn't just an abstract number. It's got a unit next to it. And well, if your formula is reasonable, if you want something that's in meters, you want a distance, the units of time should cancel. And they did, suggesting this is a reasonable formula. A lot of times, if you want to suppress the units and just communicate them in advance, well, you can leave out the units. It's -5t squared plus 20t. And let's use this formula now. At t equals 0, since time is measured in seconds, seconds is consistent with what we want to use, so I'll just plug in t equals 0. And you do some walk, yeah, of course this is 0, which makes sense. If you start on the ground, you throw the bowling ball, but you don't actually wait for it to travel any distance, the ball's still on the ground. At t equals 4 seconds, let's find the height of the bowling ball. Do this yourself and come back. -5 times 4 squared plus 20 times 4. Let's compute that out. So let's see, it's -5 times 16 plus 20 times 4 is 80. 5 times 16, all right, that's the same thing as 10 times 16 divided by 2. Right, 5 is 10 divided by 2. Well, that will be -80 plus 80 equals 0. And you know what, let's specify the units in meters, even though for 0 it doesn't matter. So it looks like it lands again. So I guess here's the question. For any time, can you determine the height of the ball uniquely? Yeah. That's exactly what it means to be a function. Here's now a formal definition. A function from some set A, usually it'll be a set of numbers, the things you can legally plug into the function, to some set B, usually a set of numbers, the types of outputs you expect to see from this function. is a rule which takes a member of the set A and gives you a member of the set B. Said another way, a function is a thing that can be determined if you know what x is, as long as x is a valid input. The word domain of a function is just all of the valid inputs. And whenever you have a model, the word domain means something a little bit more than literally what can you evaluate this formula for. It's all things for which that formula actually models what the thing is supposed to do. And in order to demo that, let's see what happens at 10 seconds. If you plug in 10, let's see what we get. We get negative 5 times 10 squared plus 20 times 10. Let's evaluate that out. Let's see. 10 squared is 100. Multiplied by negative 5, you get negative 500. Plus 20 times 10 is 200, is negative 300 meters. So now think about what that would mean. That would say if you throw this bowling ball and wait 10 seconds, it will have borrowed 300 meters below the surface of the Earth. This is definitely not reasonable. Certainly do not expect the ball to fall below height 0. Now, if the problem were different, maybe you would. Maybe you would say, well, I'm standing on a cliff. And you stand here with your bowling ball, and you throw it up and down. It'll come back to height equals 0, but then it'll keep on going down. So under different circumstances, yeah, you could understand the negative height as being meaningful. But you're not on a cliff, you're just standing on the ground up there. All right, so let's, if you only want inputs for which the height of the bowling ball is given by this formula up here, well then, what should you understand the domain to be? Well, the domain should start at the moment you throw the ball, otherwise you're predicting the height of the ball before you throw it, and you haven't thrown it yet, so it's probably at height 0 or you're still carrying it around. So this formula doesn't make sense to use then. So all times after you throw it, and then until it lands. But you know what? You know when you threw the ball. You threw the ball at time equals 0 seconds. And coincidentally, we figured out when it landed already. It lands at t equals 4 seconds. So I would describe the interval as a function as just being the interval from 0 to 4 seconds. The set of all outputs that are actually realized by a function is called its range. So all outputs that you actually hit are the range. And here's a fact that I'll give you. Well, no, that's in a second. If the height of the ball so h of t is the height of the ball at the top of the page, what's the least the height could be? Well, we've already discussed you don't expect a negative height. That wouldn't make sense. H equals 0 is the minimal height that makes sense. And you know that that height is actually achieved. It starts at 0 meters. At time equals 2 seconds, I'll give you this as a fact, the ball is at its highest. The maximum height of the ball is when t equals 2 seconds. We'll justify that in a bit. So what's the range of this function? Well, the max height is the height at 2 seconds. Because of this. The ball is at its highest at 2 seconds. And we've computed that. That is 20 meters. So you know the maximum height is 20 meters, the minimal height is 0 meters. And here's another fact that maybe I'll just give you. You don't expect the ball to teleport at any point. If it starts at 0 meters and eventually hits 20 meters, it has to achieve every height between, right? At some point the ball has to be at 10 meters above the ground, 15 meters, 5 meters, 3.2 meters. All heights in between are achieved ball doesn't have a magic telebar. So the range, so that's all outputs that are actually accomplished. Well, it starts at 0 meters, it makes it up to 20 meters, and it accomplishes every height in between. Neato. So I'm at 30 minutes, let's keep on going. All right, so I'll start waxing much more abstract now, and we'll get as far as we get. So if you have a function defined by a formula, you evaluate that function by just plugging numbers into that formula. So here's one. Here's something that's not given by a formula at all yet. For any number x, let's let f of x be the distance from 0, 0 to x1. Let's write down a formula for this. Do we have a distance formula? Yeah, of course we do. The distance between 2 points is the square root of the difference between their x values. So that's x minus 0 squared plus 1 minus 0 squared. And this obviously should be simplified because I plan on using it. All right, so here's a formula for this function. This function is given as a formula by the square root of x squared plus 1. So there are a few things you can do with functions. Oh, this is wrong. This was supposed to happen here. Chris. Let's use this to compute f of 2. So what does this mean? This just means I want to evaluate at that input. Take this and plug it in for that input x. Square root of 2 squared plus 1. That's easy enough. That's the square root of 5. Maybe you want a decimal approximation? Let's get a decimal approximation. Square root of 5, somewhere around 2.2. Nice. You can plug formulas into functions. If you want to compute f of x minus 2, what do you do to do this? Well, you replace all x's in the formula for f of x by x minus 2. And here's a useful way I find of just writing this. I'm not going to think about that x minus 2 all at once. I'm going to put it in a box. I'm going to think about what f of box means. I have a formula here. F of any input is that input squared plus 1, then take a square root. So f of box will be take box, square it, and add 1. And you know what goes in that box? X minus 2 goes in the box. All right, those parentheses matter a lot because you need to make sure you're squaring all of x minus 2. And maybe simplify a little bit. You can FOIL out x minus 2 squared. Maybe I'll go off to the side to do that. So just remember how you square things. What does squaring mean? It means you multiply it by itself. X minus 2 squared is x minus 2 times x minus 2. And you know how to expand out a product like this. You FOIL, right? If you like to use the distributive law. So use the FOILing trick that you know. You'll get x times x is x squared minus 2x minus 2x. Minus 2 times negative 2 is plus 4. X squared plus 4x plus 4. And these things are all equal to each other, so let's put some equal signs between them. So this is what just the thing that's being squared is equal to, and then I add 1. X squared plus 4x plus 5. All right, let's take g of x to be the square root and do the same. So let's evaluate f of g of x. So that'll be f of the square root of x. All right, take a moment and do that. Cool, you did it. Let's come back and go through it together. This will be the square root of x, but then you square it, and then you add 1. And let's simplify it. This will be the square root of x plus 1. Nice. All right, so here's a trick question. Let's suppose you wanted to compute the domain of this function. And here, I'll propose two different candidate answers. It's one of those two. Take a moment and select the right answer. Shoot, maybe even go into like the YouTube shtick. Comment below the answer. I don't know if I have it set so I have comments enabled. Doesn't matter. All right. So let's think about it one way which is wrong. Let's look at this formula and see what inputs we can actually plug in. Well, I see a square root. What things are you allowed to take a square root of? Well, non-negative things. You can plug 0 into a square root. Square root of 0 is 0. You can't plug a negative in, though. So you need to have x minus 1 bigger than or equal to 0. Oh, but you can add 1 to both sides. That means x is bigger than or equal to 1. God damn it. Sorry, I shouldn't swear when I'm being recorded. X plus 1 is bigger than or equal to 0. So you subtract 1 from both sides. X bigger than or equal to negative 1. Oh yeah, that's the interval from negative 1 to infinity. Well, what's wrong with that then? So here's what's wrong with that. It turns out whenever you do algebra, you might change the domain. Let's see what happens if you plug in x equals negative 1. You should always use the purest version of your function. Don't do any simplification. This was the original formula we got. Let's use that. This will be the square root of negative 1. Then we square it. Then we add 1. And now you see what's wrong. You're not allowed to see a negative inside of a square root. So here's the takeaway. You always check domain before simplifying any formulas. And the reason to do that is because whenever you do algebra to a formula, you might accidentally change the domain. Something that prevents a thing from being defined might suddenly become defined after you simplify it, and that makes the domain bigger, which is often like desirable, but it means that's really a different function. So these two look like they're the same function. They kind of are, but they have different domains. You always check the domain before simplifying. So let's get the actual right domain. So let's look at the square root of x. Then that gets squared, and then you add 1 to it. So in order for this to be defined, what do you need? Well, everything that's inside of a square root can't be negative. So because I see a square root of x, I better have x bigger than or equal to 0. But I also see this big blue square root. So I also see the square root of x squared plus 1. So that means the square root of x squared plus 1. It better be bigger than or equal to 0. And this way we can simplify it down. In fact, we kind of did earlier. X square rooted, then you square it, becomes x plus 1 bigger than or equal to 0. That becomes x bigger than or equal to negative 1. That suggests negative 1 to infinity. But you need both of these to be true. So let's draw out this domain. So I see 0 to infinity. I see also there's a negative 1 to infinity. And in order for this function to be defined, you need x values that lie in both of these intervals. And it looks like that's just everything from 0 to infinity. Nice. All right. So, I got 10 minutes. Let's talk about how to just generically compute domains of functions based on their pieces. So whenever you're given two functions, f and g, you can combine those functions to get the sum, which is just the sum of the two functions, the difference, the product, and the quotient. You can add, subtract, multiply, and divide functions in the most obvious way. The domain of a sum, difference, or product. Let's think about what this domain means. The domain is just all x values so that this formula makes sense. In order for f plus g to make sense, f needs to make sense, and g needs to make sense. So you need things that are in the domain of f and in the domain of g at the same time. So the domain of f plus g, or f minus g, or f times g, is all inputs which are in both the domain of g, f and the domain of g. And the plain language reason for this is for f of x plus g of x to sense, f of x and g of x need to make sense. Division's different though, right? If you want to divide something by another thing, well, there's a thing you can't divide by, 0. So the domain of f divided by g is all inputs which are in the domain of f and in the domain of g, and which have g of x not equal to 0. So in plain English, what does this mean? For f of x divided by g of x to make sense, f of x needs to make sense. G of x needs to make sense. And g of x had better not be 0. So let's try to do that in practice. Let's not find a formula for f divided by g, although that's easy. F of x divided by g of x is f of x is x squared plus 1 divided by x squared minus 1. If you want the domain, let's just check some things. X squared plus 1, well, is there any number that you can't square? Nah, you can square anything. You can add 1 to anything. This formula always makes sense. X squared minus 1. Same thing. Domain is all numbers. But x squared minus 1 also can't be 0. So let's figure out when x squared minus 1 equals 0. Well, that'll mean x squared equals 1. Square root both sides, so I've got x equals plus or minus the square root of 1, plus minus 1. X equals 1 and minus 1 are not in the domain. I'm going to flip to the next page and write down the conclusion. So, the domain of f divided by g for this particular f and g is all numbers except x equals plus or minus 1. And in order to put that in another notation, let's see what that means. There's minus 1, there's plus 1. But the domain is going to include everything else. So, that sentence is a correct answer. The domain is all numbers except for x equals plus or minus 1. But it looks like we can also write this as an interval. In interval notation, well, it looks like I have negative infinity to negative 1, exclusive, I don't want to include negative 1, together with, which mathematicians also use this upward-facing cup symbol for the union. So everything in this, then also everything between negative 1 and 1, together with everything from 1 to infinity. There's the domain of that function f divided by g. All right, I have 5 minutes left. I think that's actually enough time. Compute these, do that, and then come back. Cool. All right, so let's list it out. The domain of f. F is already a quotient. X plus 1 is fine. It doesn't have any gaps in the domain. If you just saw x minus 1, there are no gaps in the domain. So if you just look at the top, it looks like the domain is everything. X minus 1, just look at the bottom. The domain looks like it's everything. And let's remember now that you're doing division. Can't divide by 0. X minus 1 had better not be 0. That means x had better not be negative 1. Apparently the domain is all numbers but x equals negative 1. Play the same game with g. Add 1 to both sides. X is not plus 1. The domain is all numbers except for x equals plus 1. I apologize. Let's play the same game with g. Well, x on its own, nothing can go wrong. X plus 1 on its own, nothing can go wrong. But you see division. X plus 1 had better not be equal to 0. So it looks like x can't be negative 1. The domain is all numbers except x equals negative 1. Now I can compute the domain of f plus g without doing any work. I need numbers that are in the domain of f. And the domain of f is everything except for 1. So x equals 1 is bad. The domain of g, x equals negative 1, is bad. So what's the total domain? Everything but x equals plus or minus 1. And let's also do f of x times g of x, because something weird happens. So on the one hand, objectively you know from this line, f plus g and f times g have the exact same domain. They're just things that are in the domain of f and the domain of g. So you know what the answer has to be. All numbers except x equals plus or minus 1. And let's go ahead and do one quick check before we move on. What if you simplify? Let's see what happens. X plus 1 divided by x minus 1, right, there's f. Well, f times g is x divided by x plus 1. You'll notice something cancels. And if you want to just see this, you would say, well, it sure looks like the domain except for x equals 1. And there's a special word for such a thing. So if you can simplify a thing to get to something that has a bigger domain, well, really the domain has a gap in it. X equals negative 1 is not in the domain of f times g. But you can simplify that function. So you have a gap in the domain, x equals negative 1, that can be removed by simplifying. This is an example of what's called a removable discontinuity. And let's not think about f divided by g. Let's stick with f times g. So this has a removable discontinuity at x equals -1. It's called a removable discontinuity because if you simplify the function, you can remove the discontinuity. That's why it's removable. This isn't a one that we'll linger on a whole lot, because it's really something that's better defined in terms of the calculus. But if you simplify, you can change the domain. That's the important takeaway. If you do change the domain by simplifying, you have a removable discontinuity. Cool. So I see that I'm technically past time, so I'll go ahead and stop this. As a reminder, I won't see you on Friday, but I will 100%, well, let's say 95%, right? Bad things can still happen. Be back on Monday. Talk to you soon. Oh, and let me know if you have any questions. I'm reachable by email. I'll be emailable this whole weekend. Ciao.